Right, so the division that we were supposed to complete on Friday, I'll do it when I'm doing past paper for science, right? Let's move on. So, I'm on page 141, module 6, stress, strain, and Young's modulus. I feel like in science, we've gone over that round now, right? I feel like the worst is behind us. From here on, it's okay.
See in a month's time and we'll
it's okay, right?
You're recording.
So, yeah. So, I'm looking at module 6.
Oh, so are we doing the same thing? Taking the pulses? Yeah. Just that's what.
Okay, very easy section, very simple calculations, very simple formulas. Right? So, remind me to print my data sheet for maths for you, alright? After this. Next I'll give it for science. Right? Okay, so I'm on page 141. Nah, that's not good. For science episode. Yeah, everybody signed 2 registers before?
Yeah.
You signed what?
2.
Tell me, you signed 2.
Okay. You signed 2, yeah.
Yeah.
I'm not signing in my block that, can I?
So, direct stress. So, when a force is applied to an elastic body, it will deform or try to deform the body. The force will be resisted by internal forces caused by the cohesion between the molecules of the material, and the resistance against force is called stress. That's what you need to highlight. If they ask you what is stress, stress is the resistance against force. Okay. So, oh wait, fuck. Carry on. Right. Yeah. So, they tell you on page 141, if a bar that's shown in figure 6.1 is cut through any section X and X, each section will be in equilibrium under the external force F and the stress at that section. The stress can also be called the internal cohesive force, and the simplest form of load or force is tensile or compressive. Now, how many of you have heard of tensile before? Tensile is basically like a pulling force. You know when they try to get the minimum amount of force that's required before, like for wire, right? They want to test what's the minimum force needed before it breaks.
Yeah,
so what they do, it's a tensile strength test, right? You get a machine that holds that wire at 2 ends and it starts to pull it. And every time as it's pulling it, it's applying more force as it's pulling it. So at that point, just before it breaks, that will be the minimum tensile strength needed to break, right? So the minimum force needed to break the wire. So tensile is more of a pulling force, vertically pulling, and compressive is obviously squashing something, right? You're squashing. So your force is actually internally together. The tensile is away. Okay? You understand the concept, right? So a tensile force will tend to make the body longer. So if you look at figure 6.2, right? Can you see your forces are pulling away from where the bar is?
Yeah.
So obviously when it's pulling away, what it's basically doing? It's stretching, right? So it's going to make the body longer. A compressive force will tend to make the body shorter, because you're basically compressing something. You're squashing it, right? Now, stress is that symbol there. I don't know what the Greek name is, but stress is that symbol, and it is the force per unit area upon which it acts. So, your first formula...
Q.
Huh?
Like the upside down Q.
Yeah. No, but there's a Greek name for it, something. It's like that, and it's equal to force over area. So this here is stress, and its units is in pascals or Newton per meter squared. Okay, it's the formula for pressure. Yeah. Well, if you look at it, it is the formula for pressure. Right? But it's the force that's being applied over an area.
Opposite.
And this area is cross-sectional area. Not surface area, cross-sectional area. Understand the difference between surface area and cross-sectional area. Okay. Okay, so say you have, for example, This is the tube. Right? Surface area is basically the surface of this. Okay, so the area of this will actually be a what? The surface, if you have to calculate it.
Yeah.
It will be more of a rectangle. Alright? Understand?
Yeah.
Because remember, if you're looking at it face up, it's going to look like this.
Yeah.
Right? That should be the surface area. Cross-sectional area is all of that. If you have to cut it. Right. Okay? So if you're looking at the cross-sectional area of a cylinder, it's pi d squared over 4. Okay? So this area that they're referring to is a cross-sectional area. You'll see it in examples, right? So that's one formula, right? Then they tell you, example of tensile loads are cables, tie bars, anchor cables, etc. Examples of compressive loads are connecting rods in engines, table legs, pillars, columns, etc. Let's do an example, and you'll see how simple it is. You'll love this section, right? This is example 6.1. I never saw a very difficult question being asked for this, right? They tell you a tensile force of 30 kilonewtons is applied to a rectangular bar. So you have a rectangular bar.
Okay.
Right? Rectangular bar. So a tensile force, remember tensile force is a pulling force. So it's basically acting like this. You have 30 kilonewtons acting here and like 30 kilonewtons pulling it here. Okay? The length of the bar is 500 millimeters. And it has a cross-sectional profile of 30 millimeters by 12 millimeters. So what that means, see these lines here, this could be 30 millimeters, and this could be 12 millimeters. Okay? Calculate the tensile stress in the bar. Now, stress is equal to force over area. We know the force. Right? We know area because we can work it out. But how would you work out the area? What area did I tell you it is? Cross-sectional, not surface. If it was surface area that we use, you would have said length times breadth. Right? At this length times that value.
Yeah,
but it's cross-sectional area, so like if you have to cut the bar, whatever is facing you, what is that? So it will be 30 times 12. Okay, so our force in this instance would be equal to 30,000 newtons. The area would be equal to 0.03 times 0.012 because we're converting it to meters. You understand? Okay, so this here comes out to
0.00036 3 zeros.
0.0036
No.
meters.
3 zeros after.
Okay, then the formula is stress is equal to force over area, which is equal to 30,000 all over 0.00036, which is
8333 recurring.
833.
Yeah.
Like so many threes equal to
4 threes. 4 threes.
seven threes.
1, 2, 3, 4, 5, 6, 7.
Common 3.
That's Pascals, right? If you want to write it as a smaller number, 1, 2, 3, 4, 5, 6. You could have said 83.333 Pascals. Okay? Is that fine? Simple calculation?
Yeah.
Okay, not bad. Then example 2. Calculate the maximum allowable load on a pillar with a cross-sectional profile of 400 by 450 if the compressive stress of 5 megapascals must not be exceeded. Now, what are they asking you here? So this is example 6.2. So you have basically a pillar. Right. Now, the cross-sectional profile, this is 400. This is 450. And it has a compressive stress. So its stress is equal to 5 MPa, and the force that's acting on it is compressive. It's a pillar, right? You normally have a weight on top that's pushing it down. Okay. Now they want to know the maximum allowable load. So the force, right? The maximum force that it can hold for 5 that, right? So
Now you get the other one.
okay, so this here will actually be 5 million pascals. Yes? This would be 0.4 meters. This would be equal to 0.45 meters. Right? So this stress is equal to force over area. The stress in this instance is 5 million equal to force all over 0.4 times 0.45, because it's cross-sectional area, right? Just be that much clear with that. So you'll just take whatever number you get here, multiply it with this, and that will give you the maximum allowable load that that pillar can handle. Nine hundred thousand newtons, which is 900 kilonewtons. So anything greater than 900,000 newtons, and that pillar is going to basically break. Right? So you can handle a maximum load up till 900,000 newtons. Easy, right? Right, there's no catch in all of this. I know. You're waiting for that. Oh, then I actually was this thing. It's not like that, right? Example 6.3.
So far it looks okay. It's not.
Yeah, but in how many boxes was this? This is small.
No, stress, how many modules is it? How many marks is whole section? For stress strain in Young's modulus?
10 marks.
15. Yeah, I hope it's 15.
14.
14, man.
That's good.
Gravy this is, man. That's only 40% of your paper. Okay, so example 6.3, calculate the maximum load that can be applied to a rectangular bar with a cross-sectional dimension of 25 millimeters times 30 millimeters if the tensile stress in the bar may not exceed. So once again you have a bar, right? It's a tensile force, so it's pulling it like that. The stress they give you is equal to 45 MPa. The cross-sectional area is
25 by 80 millimeters.
So let's say this is 30 millimeters, this here is 25 millimeters. So stress is equal to force over area, right? That value is 45 million equal to force all over the area would just be 0.03 times 0.025. Therefore, your force is equal to
25 million.
33750 newtons, right? Or you could have said 33,750 kilo newtons, right? So anything greater than that, it's a tensile force, it will pull it and it will break. Now pull like this. Yeah. Okay. Right? Okay. You want to take it down? This is science now, it's not maths. You're cute, science. Please.
So that means the length of the whatever the doesn't really matter then, huh?
It only matters when you're working on strain, which you gotta see.
Oh.
And even that tree is easier form. That day is just the change in length over the original length. That's how much change it was subject to.
Yeah. Suppose then you go up early and study rather than sitting here and waiting.
Yeah. My diagrams are getting better.
Definitely. I made a comment this morning actually.
That my diagrams are horrible.
No, that my drawing was my drawing for it came up was like your diagrams.
Yeah.
This is engineering science, right?
That's so insulting.
No, but I said not the new drawings of all of it. It was a compliment.
Thanks.
I checked seconds on disaster overhead bridge they built in that they made this two bridges in Sofia, and they had a big open area, and that was the same area.
Yes,
They had dances and all that in the 60s or so. They put two overhead bridges,
Yeah.
and one below the other. The first time they built
Pillar
bridge
rope.
like this. So yeah, so what happened was the design called for one bar from the top all the way to the bottom, holding the both
Just
bridges.
one?
Just one. So these was couldn't get the one bar. So they decided no, we'll change the design. Not a big deal.
Yeah, you see what a big deal is.
We put two bars. No, puller broke, so they put two bars, but now there was supposed to be one bar, with one nut holding this bridge and one nut holding that bridge. Right, so they did the calculation. The top stress on that bridge is only holding its own weight. Right, and then the bottom one to hold its own weight. Because the rod was supposed to stay. Right. Oh no, it was screwed in the nut. They could get the rod, but because to get to the top bridge, they had screwed all the way from the bottom one all the way to the top. So that we cut the rod and we make two holes there. So when they did that, now that top nut was now only the weight of the bridge, only the weight of the bridge plus the weight of the bridge at the bottom. So it pulled.
You're gonna do something like that now. It's called shear stress. It's a pulling stress. See this one here, it acts vertically. You pull vertically, or it acts horizontally. The other one is more of a sideways force. Like so, if you have this block, this right, and if I join it by this marker, right, and I start to pull the aircon remote, and I start to pull it again, this here is eventually gonna break.
Yeah.
Right? Same thing if it was like this. It's going to cater force, downwards force and upwards force. Once the shear, the stress that's the two things. That's the one, yeah. You got it, guys? This side, you got it?
Is that John's modulus?
No. That's
Oh.
shear stress.
Oh.
Okay. Example 6.4. Right? So example 6.4, they tell you that a compressive force of 50 kilonewtons is applied to the object shown in the figure below. And this is what the object looks like.
Oh, so now it gets a little more.
So straightforward.
So simple. Yeah. Tell you a compressive force of 50 kilonewtons. So basically, this object is against the wall, and you're applying 50,000 newtons against it, right? Calculate the compressive stress in each part. So you got two parts. You got part P and you got part Q. What does the symbol mean? Diameter. Right? That symbol, circle with a cross in the center, but with the line going through. I don't think I am. Yes, I am. I never stopped recording. Right. So diameter, that symbol with the circle with the line going through, right? That would be diameter. So looking at it, what would be the cross-sectional area in terms of, so this is basically a cylinder, right? Cross-sectional area of the cylinder is
Pi d
pi r squared or pi d squared over 4. That will be the area. And the force that's being applied to it is 50 kilonewtons. So you just work it out, right? So you'll see for part P, the area of P is equal to pi d squared over 4. This area is equal to pi times 0.05 squared all over 4. Because this is 0.05 meters. And watch it.
.00196.
Right? That's the area. So its stress will be equal to the force all over the area. So its stress will be equal to 50,000 all over 0.00196, which is
0.08.
Says 25, approximately 25.510. Okay, so that's the compressive stress in part P. You'll understand what I did there, guys? Not difficult. We just worked out the area of the cylinder, cross-section area, divided it by the force being applied. We got the stress in part P. Now, let's do for part Q. So, area of part Q is pi d squared over 4, which is pi 0.02 squared all over 4, which is
0.000314.
0.000 meters squared. Right? So its stress will be equal to force over area. Same force is being applied of 50,000 newtons all over 0.000314, which is
159.
yeah,
235,668.8.
which is
159.
159.236. It's easy, right?
How come they decimals off here, all the regions in?
Probably they took the whole thing as see when you got the area value, they just took 50,000 over ants. So they took it with all the decimals after. Okay, so stress is not no stress. Stress is no stress. Right? I can take out this set, right?
Yeah.
Okay. So let's move on to strain. Right? And strain is also not difficult. So, on my direct strain on bottom of page 144. So they tell you that if the material of an object is subjected to a tensile force or a compressive force, stress is produced in the material and its length is obviously changed. Remember, with a tensile force, it's a pulling force. So whatever its original length was, it will now become longer. With a compressive force, it's more of a squashing force, it's going to become shorter. So an extension of length will take place in the case of a tensile force, and a reduction of length will take place in the case of a compressive force. We all understand that, right? Yeah. Then we get this formula for strain. Strain is defined as the change in length per unit length. Okay, you can highlight that as definition. And they come out with the formula for strain of this is equal to change in length. Okay, so that's strain. It's equal to the change in length all over length. There's no units for it because you're going to end up with the same unit being divided by the same units, right? So it's a dimensionless quantity. Okay, straightforward. Okay, let's do an example. Example 6.5. Okay, so for example 6.5, they tell you that a metal wire is 2.5 meters long. It's 2.5 meters long and it has a diameter of 3 millimeters. Okay. A tensile force of 20 newtons is applied to the wire and it stretches by 0.25 meters. 0.25 millimeters. So, if I had to draw that, assume that the material is elastic, calculate stress. Okay, so this is the information they gave you, right? You originally had a piece of wire that is 2.5 meters long. Okay, its diameter is 3 millimeters. So what happened was they applied a tensile force. So they grabbed this end, they grabbed that end, and they started pulling it. The force they applied to pull it was 20 newtons, right? Remember, because it's a pulling force, it caused the length to increase. And how much it increased by? 0.25 millimeters. So what will be its new length? So this here is 0.00025. Yes?
How much is it? 2.5. Oh, shit.
No, I'm saying this, the 0.25 millimeters to meters is 0.003
zeros.
Yeah. So this is now the new length of the wire is actually 2.50025. Right? I understand the concept of it. Okay. So, what's the question?
Force. Stress.
Calculate the stress in the wire. Now, stress is equal to force over area. We know the force is 20 newtons. It's force over cross-sectional area. So it will be force over pi d squared over 4. Yes? Okay. So this here is actually 20 newtons all over pi. Your diameter is what? 0.003. No.
0.203.
0.003 squared all over 4. And your stress is now
2829421.
2.829.421.
0.211.
Okay? Or you could have said if you answered 2.829 megapascals. Okay? That's stress. Then they ask you to calculate the strain in the wire. Now what's the formula for strain? The symbol for it is that equal to the change in length all over the original length. What's our change in length? 0.00025 all over the original length, which is 2.5. You get an answer?
No, we
0.0001.
0.001. Right? That's your answer.
My calculator is so lazy. It doesn't give me these zeros. It gives me to the exponent.
So you go shift 9.
Yeah, but no, but it's only give you to the it's also giving you exponents.
No.
What's doing it? Hey, what man?
I think you would throw the files, smash it. So it'll be
My one also does that. It also gives me the graph. My one don't even give me the graph values like yours. Yeah, I got mine for like 10 years.
oh, yeah.
But you can write your answer as 1 times 10 to the minus 4. It's fine.
You don't have to change it.
You put it into
Don't you press this button here to change it?
yeah.
The ENG.
Huh.
Can you get your answer? Press ENG.
Where the heck is that ENG?
Just there. Huh? You need to see.
Okay.
No, but it keeps on. You need to shift it.
Shift ENG. Yeah.
So you'll shift it one more time, and then you'll see 0.0001. Just don't, but just write your answer as exponent, it's fine. Or if you know how to convert it into this thing, then just do that. But that's maths, right? This is science. Concept. You'll understand.
Yeah.
Not difficult. 2 formulas so far. What are the 2 formulas? Like this, the stress formula, strain formula. Let's do another example. They tell you a steel bar.
So there's no unit you say for that.
Yeah. Because remember the units will cancel.
Cancel out.
Okay? So they tell you a steel bar has a cross-sectional dimension of 5 millimeters and 10 millimeters. So if this is your bar, then this is it's 2 meters long and it is compressed, so the force the deformation is 0.35 millimeters. So let's just say deform to calculate the stress. So remember with compressive force, so that's the information, right? Your bar was originally 2 meters long. With compressive force, you're basically squashing it. So if the bar is going to come out shorter, right? They basically told you that it now became 0.35 millimeters shorter than what it was. Okay? So they want to know the stress, compressive forces are being applied. So stress is equal to force all over area, right? So what is substitute?
30 kilonewtons, 30,000.
0.0.
30,000
Actual meters.
Oh, it's
30,000 times pi divided by pi diameter.
Huh?
There's no diameter.
No, it's 0.5.
I like how he said that. He said, no, so it'll be 30,000 divided by pi times diameter. Diameter? There's no diameter there.
At least I corrected myself.
Oh my goodness, that's what's happening.
See,
Sure. Go ahead.
that's what you get for breaking fun of me.
Yeah. So this would be 0.01 times 0.005, which is
600
600
million.
600 million.
Yeah.
606 zeros.
Pascals, right? Which you could have said was
688.
okay. Stress, strain. Then the strain.
Yeah.
Okay, strain is equal to change in length all over original length. Your change in length would have been 0.12335. Yes?
Yeah.
All over 2, which is you converted this into meters.
No.
0.000175.
No, yeah, it's right.
Wait.
It's right.
That's right.
It's right.
0.30175.
These ones are wrong.
7.5.
No, these ones are right.
How are we wrong, Chandler? They got the right answer here?
Yeah, they got the right answer, but they got 0.35 divided by 2,000.
Yeah.
They made the meters millimeters.
Okay, they changed the other one.
Because remember, it's ratios.
Yeah, so
Okay.
You still
Well,
got
they
to come
change
out
the
with the
top one,
same
only change
ratio.
the bottom one. Okay.
Yeah, but it's easier to work with the. But if you start now changing your units, somewhere along the line you're gonna mix it up and mess it up. You rather just stay with the.
Are they gonna break me?
Why are you lying to us?
Why this couldn't be the black one?
It'll come out.
Why are you lying to us? Mothers don't tell the son anything. They come covered with blood. Good.
Mother would put your blood on yours. Right. That was stress and strain. Anybody confused about it? Not bad at all, right? Compared to all the other calculations we did, this is like a
This is the easiest.
this is a break, right? Now let's move on to unit 6.2 on page 146. Shear stress. Not stress, shear stress. So, shear force is a force that is applied sideways onto a material. It's not applied vertically, it's applied. So remember with the other one, we basically like either pulling it like this or pulling it like this. This is applied sideways. So what that means, situations where a shear force would occur is wooden block A attached to wooden block B by means of a nail. So the scenario is this, right? If this is not rubbing, this is block A, block A, block B, right? This is this, it's attached by a nail, right? Now what happens if you start pulling one block and you start pulling the other block? Eventually your nail is not going to be able, if for this to start pulling, this nail needs to crack. So we're basically now calculating the shear stress that's needed to obviously take this. So like normally when you have two, like they said the wooden block one, they give you another example of a pin or bolt that's in between a load, right? So normally you have something pulling it down and then this bolt is holding the two parts together. So you basically calculate how much force that can that bolt hold before it will eventually break. You understand the concept, right? Okay. The formula for this. Can I take out this?
Yeah.
Right? for shear stress is so it's still F over A, but your symbol changes. It's the shear load over the area that's resisting shear forces. Okay? So it's still torque is equal to F over A. Right? On the next place, not torque, sorry, I said torque. I'm so used to that symbol. It's that symbol, no, that's a symbol fade, but right? Shear stress, that's the symbol.
It looks similar to torque.
Yeah, talk like that.
Yeah. They ran out of symbols. Right? So, okay, I'm on page 147, right? That's your formula. It's the exact same thing. But you all need to be able to identify from the question that they ask you whether it's shear stress or whether it's stress. Right? And you'll see how you would identify, because in a stress question they normally use tensile or compressive. The word is tensile or compressive. If you don't see it, then you know it's going to be shear stress. Right? Okay, they give you a whole examples of different types of places where you will find it. Right at the bottom, they give you that shear stress is equal to force over area. And the maximum shear stress of the plate will be equal to F over A, where F is equal to a minimum amount to cut it. Shear strain, right? When an object is subject to shear stress, the stress is represented, the strain is represented by the symbol, and this is the symbol. It looks like how the diameter thing looks. That's another problem. I don't know, whoever made the section never put much effort into this whole thing, right? Whatever was the easiest thing for them, they just... Okay, and even in this instance, X is still the change in length and L is still your original length. They just use these different symbols to, it's the same formula, it's just different symbols to distinguish between the two. Okay? Okay. Now, they, I can't even read now. Example 6.7. You're okay, right? So I only gave you 4 formulas, right? Sheet of metal, 5 millimeters thick and 500 millimeters wide, is cut by a guillotine. Calculate the force that is needed if the ultimate shear stress is 60. So pretend that it's a page, right? Very thick sheet. It's 5 millimeters thick. It's 500 millimeters wide. It's cut by a guillotine. So guillotine basically cuts it like that, right? Calculate.
Well, they don't keep cutting that. The 500 mil. That's why they give it 500 across.
Yeah. Yeah, you can say that, or you could have even said it.
The side is 500.
See, this is the length. Right?
Yeah, that's the length.
Let's see. This here is
500.
Right? Calculate the force that is needed if the ultimate shear stress is 60 MPa. So, 60. That's the information they gave. Still the same cross-sectional area. Right? So, this is equal to force over area. This is 60. Million. Force all over 0.00.
7 zeros. Oh, okay.
Right? And your force is equal to. So yeah, you understand what I'm doing, right?
Yeah.
The information that was given to us,
Yeah.
they gave you the dimensions for the cross-sectional area. They gave you the shear stress. They want to know what's the force required, basically.
So how would you know if that guillotine you had was to cut it like that or wasn't going to cut it diagonally?
They never give you the length of the sheet.
Okay.
So it's 50,000. 50,000.
50,000.
15, 1 5.
That's exactly right.
150,000.
150. That's one. How's one? Right? And that's approximately 150.
Oh. Oh, you changed things.
Change what? I never changed it.
Zeros.
Never changed it.
Ah.
Right, guys, it's easy. I promise you, I'm not even gonna lie to you. It's not gonna get harder than this. Yeah, don't trust me. I wish I told you that it got harder.
You come with this.
I know.
Yeah, I hope I don't lie. Right, I can take us up.
Yeah.
Okay. 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 Next. They tell you that? Okay, an example is 6.8. Hmm?
Stop messing with
Yeah.
it. We keep changing it.
Are you scared of each other? You have two strips of metal that are held together by a rod of diameter 12 millimeters. You can see the diagram, right? Bottom of page 148. Okay? So, the maximum shear stress for the pin, so that the rod's diameter is 12 millimeters, right? So, when you're working on the area, it will be pi d squared over 4, right? The maximum shear stress for the pin is 55 MPa. Calculate the force that is required to break the pin. Okay? So, all this will be is, this is equal to force over area. Force will be equal to the shear stress times area, right? Which will be equal to shear stress times pi d squared all over 4 cross-sectional area of that rod. But remember that two sheets will start to pull. It's going to see what force will crack the clip. Okay? This would be 55 million times pi 0.012 squared all over 4. So remember, the only time you will do stress and strain is if they tell you tensile or compressive force. Shear stress and shear strain will be in instances where your force is being applied to something sideways. Okay? So Lisha, what is it?
6220.
6220.2.35 newtons. Right? And if you want to write it kilonewtons, it will be 6 comma. So this is the force, minimum force needed to break the pin. And obviously, yeah. Guys, it's not difficult, guys. Not difficult at all. Until it gets to not working. But it's not gonna be right? Okay. Will you believe me if I tell you we're halfway through the section?
Yeah, that's the problem. We always start with easy.
No, there's nothing harder than this. Young's modulus is stress over strain. There is a graph, but that I don't know whether you like it or what, but I like it. But that day you just mainly need to learn how the graph is, how it looks. Okay. Double shear, right? I'm on page 149. Double shear is obtained where a pin joint is supported at both ends, and this is called, I may not pronounce this correctly, but I think it's a clevis and a clevis pin, right? So a clevis is a U-shaped piece of metal at the end of a beam for attaching tackle, etc. If you look at figure 6.19, right? See that U-shaped thing?
U-bolt.
That is a clevis. Okay? They give you more of a schematic representation on 6.18. On 6.19 you see the actual thing. So remember, the force that's basically pulling on the clevis would be distributed equally amongst both ends. So if it looks like this, it normally would have a hook that's pulling it up, right? Now when it's pulling it up, it has a force that's basically pulling it up there. That force that's pulling it up will be split equally amongst these two ends. You agree, right? Okay, so that's basically the operation of it. So how would you use this in a calculation? For double shear, all you need to do is your formula. Can I take it? That's it. Right? This is for double. Does it say stress? No, just double shear.
Double shear.
Yeah, double shear. When you're working out your stress, no? When you're working out your shear stress, it will be force all over 2 times the area. Okay? That's the only difference. So for double shear, it will be force times force over 2 times the area. Okay? If you look at the example, okay, this is your that clevis, right? That U shape. Now, whatever you want to hook it onto, like just say that piece has a connection like this, it will fit into the U shape, and then you would normally bolt it there, right? So we're basically working out what's the stress or the strain that would affect this bolt. So the stress we're talking about is what force would cause this bolt to crack. But remember, the force will now act on it at 2 places. So that's why we say 2 times the area. You understand? Okay. You understand? Okay. So this instance here, it has a maximum force of, so that the force that's pulling it up is equal to 80 kilonewtons, right? If the maximum shear stress allowed on the pin is 50 MPa, calculate the diameter of a suitable pin. Right? Now, how would we do that? So start with your formula as normal, right? Shear stress is equal to force over 2A. This is because of double shear, right? In this question here, okay, because they told you in figure 6.1H, you'll know it's double shear, right? If they remember, try to remember that word cleavers, right? Because it's most of the time they'll ask you with that word. If they give you that word, you know it's double shear. If they tell you tensile force, what would it be? Stress. If they tell you compressive, it's stress. Any other situations where you have a sheet of metal with a ball connected to it, shear stress, shear strain. You'll understand that? Yeah. Okay. Yeah, so this year 50 million is equal to the force, which is 80,000 all over 2 times the area. We don't know the area because they want the diameter. We're going to use the area to work out the diameter. So your area would be equal to 80,000 all over 2 times 50 million. Right? I just made A the subject of the formula. Okay? So your area would be equal to
0.8 meter cubed.
0.8
Meter squared.
That's all. Yeah. Okay. Now, with the pin, remember it's a cylinder. Then cross section area will be pi d squared over 4. Okay. That's good. That's good.
0.008.
So why are you keeping quiet about it?
Oh, my goodness.
Why is it?
A1.
3 zeros.
What's wrong with this? Misleading us.
Right. Yes? Yes, Jeff, that is the answer. Thank you. Okay. Now area is equal to pi d squared all over 4. We want to work out the diameter. So this will be 0.008 equal to pi d squared all over 4. And your diameter of the pin would be, so you multiply it by 4, divide it by pi, and square root that answer. The answer they got in the textbook is wrong.
.0319.
Yeah. So the answer is 0.0319. It's difficult, eh?
So 32 moles
Yeah.
per meter.
When you convert it.
So if we give you something that's like normally on a U-boat, you have one side thicker and the other side a bit thinner because it's threaded. So if you're working out there, then you use.
You won't say 2 times the area because it's not constant area. But it will be the force divided by the area of the one side plus the area of the other side.
Yeah, but won't you now work out with the smaller diameter because that will give way first?
Not necessarily. The force would still be distributed equally amongst both sides. It's just that you.
The smaller diameter shear first.
Yeah, but because you can hold a lower surface area. That is why you be first.
Yeah.
But when you. Wait, what you asking for? Solve for the diameter or for the stress or for the
The
force?
shear force.
Or what will break first? Or?
Yeah, what would be the shear force?
Oh, the smaller one would break first because of the smaller area that you can.
So you work it out, you use smaller area as your.
Yeah. Yeah. That should be. That should be. lot to me, right? Let's stop here for today. Tomorrow I'll do for science Hooke's law and Young's modulus, which is not bad because Young's modulus is just stress over strain. Okay, and then for shear forces, it would be shear stress over shear strain. Okay, then they ask you about stress strain graphs, but that's a very standard thing. It's not difficult. Yeah. Then that's it for module 6.
And then this module 7 there.
Module 7. Module 7 is not bad. Module 7 is heat, so thermal expansion. Their constants are given to you. Formulas are similar to this, but it's very easy. It's like plug and play formulas.
All these formulas will be on the sheets or?
I need to double check. Oh, yeah.